Hello everyone, my name is Mohammad Naseri. I'm a research scientist at Flower Labs and a PhD student at University College London. Today I'm going to present our paper BadVFL Backdoor Attacks in Vertical Federated Learning. This is a joint work with Yu Han and Emiliano Di Cristofaro. Federated learning is a collaborative machine learning technique where multiple participants train a model without sharing their data with each other. Instead of sending data to a central server, each participant trains the model locally on its own data and then only shares the model updates with a central server. The central server aggregates all these updates to improve the global model. This process is repeated iteratively until the model converges. Federated learning can be categorized in different types based on the data homogeneity across different participants. These categories are typically referred to as horizontal federated learning, vertical federated learning, and federated transfer learning. In horizontal federated learning, datasets share the same feature space but differ in sample space. In vertical federated learning, datasets share the same sample space but have different feature space. And finally, in federated transfer learning, datasets differ in both sample and feature space. As an example of horizontal federated learning, we can consider hospitals that want to train a model. They have the same types of medical records, that is the same features such as age, blood pressures, etc., but different patients, that is different samples. However, one limitation of horizontal federated learning is that data is not always homogeneous across participants. One example could be a bank and an e-commerce company that want to collaborate. They have data on the same customers, that would be same samples, but the bank has financial data, some features, and the e-commerce company has purchase history, some other features. The first step in vertical federated learning, or VFL, is the user ID alignment to securely match and align the entities, for example, users, customers, across different participants' datasets. And in VFL, there are generally two variants based on how the model training is structured: VFL without model splitting and VFL with model splitting, which is the variants we use in this paper. So in VFL with model splitting, the server hosts the top model, and each participant hosts a bottom model, which acts as an encoder to transform the raw features into embedding feature vectors. The feature embeddings generated by the participants are sent to the server. The top model on the server uses these feature embeddings as input and maps them to the corresponding class labels. Federated learning is a data minimization approach, and the model updates exchanged between clients and the server can be the root cause of various attacks. These attacks can be categorized into privacy and robustness attacks. In this paper, we focus on the latter category. Prior research has primarily examined attacks in horizontal federated learning with limited investigation into vertical federated learning. In this work, we propose backdoor attacks in vertical federated learning. In backdoor attacks, one or multiple participants act as attackers and modify their training data to introduce backdoors into the global model. And they do so by inserting a trigger into the model to make it misbehave on specific data samples with the trigger. In this example, the green square is the trigger inserted into the image to change its label from stop sign to speed limit. Unlike horizontal federated learning, backdoor attacks in vertical federated learning are challenging, as the malicious participant doesn't have access to the loss function and training labels. Only the server can define the loss function to train the top layer classification module, or modify the architecture of the top-layer classifier function. Furthermore, the malicious participants cannot directly access or modify the training labels used by the server. To address these challenges, our novel attack, which we call BadVFL, follows a two-stage attack pipeline: a model extraction stage and backdoor trigger insertion stage. In this stage, the attacker collects labeled or partially labeled auxiliary data instances sharing the same label space as the training samples. It feeds these instances to the bottom model to produce feature embeddings. It trains a classifier using the feature embeddings and the labels of the auxiliary data, and this will act as a surrogate model to the top model. And finally, it chooses a source and target class. In the trigger insertion stage, it follows the clean label backdoor strategy as there is no access to the labels. The goal is to force the feature embeddings of the samples embedded with the trigger signal in the source class to move close to those of the training instances in the target class. Here we can observe an example where we have two participants each holding half of the image, and the attacker injects a trigger in its half of the image with the purpose to make the model labels this dog image as a cat. We use two-party and multi-party settings for our experiments. We use CFAR10, CFAR100, Scenic 10, and Creto datasets. And there are four main factors that we need to consider in our experiments. The first one is about which round to perform the attack and stop the label inference phase. The second one is about which classes to choose for the source and target classes. This third one is about the percentage of data points that needs to be poisoned. And finally, the fourth one is about the window size and the position of the trigger. Next, we experiment with random versus optimal selection of source and target classes. In optimal selection, the attacker computes the average pairwise distance between the training data points in the two classes, and the value denotes the distance between two classes of data points in the embedding space. The adversary repeats the process for every pair of classes and eventually finds a pair of classes with the least average pairwise distance. So here we can see that in CFAR10 dataset, in random selection of source and target classes, we use airplane and automobile, and in optimal selection we use dog and cat. And we can see that in optimal selection the attack success rate is increased. The other factor is poisoning budget, which is the percentage of data points that are going to be poisoned. Obviously, we can see that when we increase the poisoning budget, the attack success rate is also increased. However, the main task accuracy is decreased. Next, we experiment with different trigger sizes for image datasets. So here we have trigger size 3 by 3 pixel and 5 by 5 pixel. As we can observe, when we increase the size of trigger, the attack success rate is also increased, but the main task accuracy is decreased. The next factor is the position of the trigger. We experiment with both random and using saliency map approach, where the adversary computes the Jacobian-based saliency map of the training images using the locally trained classifier. The adversary uses a 3 by 3 or 5 by 5, depending on the size of the trigger window, to deliver a pass over a source training image. and then the attacker chooses the sliding window with the highest average gradient magnitudes to inject the backdoor trigger. We also experiment with a collective backdoor attack executed by multiple attackers. We first break down a trigger pattern into sub-trigger patterns and inject them separately into the data samples of each participant controlled by the adversary, following the label inference and trigger injection stages. In the testing phase, we inject all the sub-triggers into malicious participants in parallel to conduct a backdoor attack. Please refer to the paper for the results. We experiment with three potential countermeasurements: neural cleans, differential privacy, noise, and anomaly detection. In neural cleans, server identifies candidate neurons that may be involved in a backdoor attack by analyzing the network's behavior on different inputs. Then it uses a pruning algorithm to remove these neurons from the network. However, since in our proposed attack, the server takes feature embeddings as input and not the trigger images, then neural cleans cannot defend against the backdoor attack. Another approach is DP noise, where the server adds noise to the feature embeddings submitted by the clients. So here in the plot, we can see that when we increase the variance of Gaussian noise, the attack success rate is decreased. And for the third defense, we consider performing anomaly detection over the feature embeddings of each class. In our backdoor attack, the attacker replaces some of the training data points belonging to the target class. So the server could perform anomaly detection on the feature embeddings of the same class submitted by each participant. And we can observe that in CFAR10 datasets, using anomaly detection countermeasurements actually decreases the attack success rate. So in summary, we talked about different variants of federated learning, and we selected vertical federated learning. We proposed a novel backdoor attack in vertical federated learning, and we experimented with different datasets and presented different factors that are needed to be considered for performing the backdoor attack. And finally, we talked about potential countermeasurements against the proposed attack. Thank you.